Okay, jot down this example. So here's an example where we're actually given an equation. So this time we don't need to figure out what the equation is. We're given an equation relating x, y, and z. And the instant of interest is when x is 1 and y is 3. We're told x is decreasing at a rate of 2 units per second. So dx dt would have to be negative 2 units per second, right? Negative because of the decreasing word. And y is increasing at 2 units per second, so that's referring to another rate. So dy dt is 2 units per second. We're trying to find, again, make sure you're writing down what it is you're trying to find. Trying to find the rate at which z is changing, so that's dz dt. And then once we're done, we want to know is z increasing or decreasing. So here's our equation. And just like before, we need to differentiate each side. So the derivative of z is dz dt. All right. And we're going to need our product rule. So let's attack this using our product rule. So we're going to have 4y cubed. I just took the derivative of a y term, so I need a dy dt plus, and then, oops, I need to remember, not plus yet. I need my x cubed, right? That's the other part of this left alone. And now we're going to leave y to the fourth alone and take the derivative of x cubed, which is 3x squared, and then we need a dx dt tacked on to that. All right, so that's probably the hardest part of the problem, just recognizing that we need our product rule. And from there, we're just going to plug in all of the pieces that we know. So the y value of interest is 3, all right, and then dy dt is 2. The x value of interest is 1. All right, so we're just going to carefully substitute all this in and then clean it up. So when we do the rest of this, again, just carefully substituting in. You'll be allowed to use a calculator for this. All right, we end up with negative 270 units per second for the rate at which z is changing. Now, because of this negative, it means that z would be decreasing. Okay, on to the next one. All right, so in this question, we're talking about a 13-foot ladder. It's leaning up against the wall, so here's our wall, here's the ground, and then this will be our ladder. So that's a fixed distance of 13. All right, the ladder is always 13 feet long. The bottom of the ladder is slipping away from the base of the wall at a rate of 2 feet per second. So let's let this distance be x and this distance be y. So the bottom of the ladder, so here's the bottom of the ladder, okay? It's slipping away from the bottom or the base of the wall at a rate of 2 feet per second. So that's describing dx dt. Okay, so it's increasing because it's getting further and further away from the wall. So visualize this ladder slipping away. Okay, now as it slips away, the top of the ladder, so right here at the top of the ladder, that will be slipping down the wall. Okay, so the ladder will be coming down. So we're trying to find how fast is the top of the ladder moving down the wall. So we're looking to find dy dt. So that's the rate at which it moves down the wall, okay, when the bottom of the ladder is 5 feet. So x is equal to 5. Notice we're not told directly what y is equal to. So at this precise moment, when x is 5, y would have to be 12. Isn't that a nice Pythagorean triple, right? Usually you'll see nice Pythagorean triples in these problems, right? 5 squared plus 12 squared would give you 13 squared. If you're not sure how to find that, you'd have to do Pythagorean theorem. So now we need an equation relating all of these pieces here from the problem. Again, I'm going to label the 13 because that is a fixed distance. I'm not going to label the 5 or the 12. Those are not fixed distances, okay? X and Y is what we have on our picture here. So we need to come up with an equation relating x, y, and 13. Well, we're talking about sides of a right triangle, so hopefully what's coming to mind is Pythagorean theorem. So now let's take the derivative of each side. So 2x dx dt plus 2y dy, dy dt equals, now 13 squared is 169. The derivative of that is just 0. So from there, just plug in all of the pieces that we know. Alright, so go ahead and do that. Hit pause. So hopefully this is what you got. So you just plug in those pieces. We're trying to solve for dy dt. Notice how our rate is a negative number, which makes sense because we know that this ladder is coming down. It's also going that way, okay? So we would expect that rate to be negative because the distance, or the rate at which y is changing here, it's negative. So think of it as it's a vector. All right, this negative is telling us the direction. Okay, it's going down in this case. Okay, it's decreasing at a rate of 5/6 feet. All right, that's for y, every second that goes by. So every second that goes by, y is going down by 5/6 feet. Okay? Okay, last example in this video. It's another ladder question. We have this 13-foot ladder once again, leaning up against a wall, so we know we're going to have a right triangle. And we have this bottom end, all right, it's drawn away from the wall, so I'll just use an arrow to indicate the direction. All right, so it's being drawn away from the wall at a rate of 3 feet per second. So we're talking about the bottom. All right, so we're going to just call that x. And we know that dx dt, the rate here, is 3 feet per second. Now, don't be quick to label the other side y. So let's look at what else they want us to find. We want to know how fast is the angle of elevation. So your angle of elevation is actually right here. Let's call that theta. How fast is the angle of elevation changing? So that would be d theta dt. So that's what we're trying to find, right? So we want to know how fast is that changing at the instant when the bottom is 5. So that's referring to when x is 5. So there's no mention of the other side, which we called y before. We're not trying to find the rate at which y is changing, okay? So we don't care about that. So don't label it y, because you might be tempted to use Pythagorean theorem. You have to look at what's given and what we're trying to find. We're given the rate at which x is changing, and we're asked to find the rate at which the angle of elevation is changing. So we have to come up with an equation to relate this x, this theta, and this 13. Well, you need to think about trig and your trig relationships here. So we're given essentially an adjacent and a hypotenuse. So hopefully you're thinking that's cosine. So the cosine of our angle is equal to the adjacent side over the hypotenuse. Okay? So understand that before we're quick to use the quotient rule here, x over 13 is really 1 over 13 times x. Okay? So let's find our derivative. So we know the derivative of cosine is negative sine of theta. So we have to tack on a d theta dt, since we just took the derivative of a variable of theta. And then on the other side here, the derivative of 1 over 13x would just be 1 over 13 with a dx dt tacked on. Okay? So from there, let's fill in all of our information that we know. So let's see, we have the negative sign. Uh-oh, I don't know what theta is. So let's pause for a moment and think about how we can find theta. Let's draw another picture, and this time let's draw it at the precise moment when x is 5. Okay? So what we have to figure out is what is the angle when x is 5. So to get our angle, we have to do inverse cosine of 5 over 13. So go straight to your calculator, find out what that is. So we get 1.1760 radians. Okay, make sure you're in radians. So from there, let's fill it in here. So that is our angle. So we have negative sine of 1.1760. We have that d theta dt, and then equals 1 over 13, and then our dx dt we were told is 3. So to get our d theta dt alone, just divide over that negative sign of that angle. And when you do that carefully in your calculator, you get negative 0.250. Okay? So let's think about our units here. This is the rate at which the angle is changing. So this is in radians per, what are we talking about? Seconds. Okay? So this would be our final answer. This is the rate at which the angle of elevation changes at the moment that x is 5. And the fact that it's negative should hopefully make sense to you. If this ladder is moving away from the wall, all right, that angle is kind of collapsing, so we would expect the rate at which it's changing to be negative, right? The angle is decreasing, in other words.